Hi everyone, thank you all for coming. Thank you Code and Supply for having me. My name is Philip Thompson. I'm a contributor to the Apache Cassandra project, and I'm here to give you a brief introduction to Apache Cassandra. So what is Cassandra? It is one of the most popular NoSQL databases, and by many metrics, one of the most popular databases in the world right now. So for those of you who aren't familiar, what is a NoSQL database? So it's another take on data stores that takes us away from the relational model, which is what many software engineers and developers spend their whole lives using. SQL Server, MySQL, Oracle, Postgres, these are all relational databases. And they allow us to do things we assume all databases do, which are joins and queries across arbitrary columns and store your schema in normal form and things we think of as being inherent to databases. But there's an late 90s, early 2000s concept of NoSQL, which is either not only SQL or anti-SQL, where here it really means anti-relational, because most of these databases would eventually come to adopt SQL, the structured query language. And these are data stores that primarily were key value. They were non-relational. So you could store large amounts of data and associate them just with keys and query based just on those keys. And it was an interesting model. There are NoSQL databases like MongoDB, which is a document store, which there was Google Bigtable, which is a column family, which is what Cassandra was based off of. There are things like Couchbase and Redis, which are just key value stores. So Cassandra was written in 2008 by Facebook, open sourced and given to the Apache Solver Foundation when they decided that they did not want Cassandra and they simply wanted to stay on Apache HBase. And in 2010 is sort of when Cassandra got out of Apache's incubator mode and became a full-fledged project. And so it's about a 6-year-old database as far as active development goes. So what is the concept behind Cassandra? And it is a database that is designed for availability and scale. So Cassandra was written originally to back Facebook's Messenger platform. And the thought was that they didn't particularly care about consistency. If I wrote you a message and you didn't get it for minutes, that doesn't matter as long as I never lost the message. We didn't particularly care about latency. We just needed to be able to handle throughput. And we didn't want to accept any downtime. So coming at a data store with a no downtime policy always available led to interesting design decisions. And some of those are abandoning the concept of a master. So a Cassandra cluster is a series of Cassandra servers, at least 3 up to the hundreds, even above 1,000, and these nodes that are all peers within sort of one larger data store. Cassandra's I'm going to step in more into the cluster architecture throughout this, but Cassandra is actually a very popular database. It's like 8th right now on DB Engine's ranking. It trails only Mongo in terms of NoSQL popularity. It's in a large amount of the Fortune 100, and it's gaining a lot of popularity nationwide, though admittedly most of that's centered in New York and the Bay Area. So how does Cassandra look performance-wise? So one of its key features is linear scalability. So when you have a Cassandra cluster of 6 nodes and you need to handle twice the throughput, you buy 6 more servers, you make it a 12-node cluster, and it can handle twice the throughput at the same latency. Sounds trivial, but that's actually a really amazing technological breakthrough, because if you have a MySQL server and you need to handle twice the throughput, how much bigger do you make that box? You can't just double the RAM, double the CPU, double the storage. It's not going to make it twice as big. They'd be able to do this sort of for future broadcasting to know how big you have to scale a cluster to handle what kind of load, and the ability to make that flexible. So if you're, say, a retailer and on Black Friday you need to handle 5 times traffic, at the beginning of November you can blow up your cluster, and then at the end of December you can spin it back down. So there are benchmarks linked up here. Cassandra is essentially the fastest database as long as you're willing to throw boxes at it. That's a use case dependent decision depending on what your workload looks like something simpler like Redis might be right for you, or you might not be able to handle leaving a relational model, in which case you would never want to step off MySQL or Postgres. Here are some numbers from Netflix showing their cluster size as it grew and the kind of writes per second they're able to handle. Some tweets from a company called Outbrain, and they had an entire data center destroyed in Hurricane Sandy, and their application didn't go down, and that's the result of Cassandra's architecture because it's able to seamlessly handle the loss of a large number of servers up to, depending on how it's structured, up to half. As long as you keep half of your cluster alive, you can continue serving writes and reads. So what does Cassandra look like that it's able to do this? So in order to store data across multiple machines, we have to partition it somehow. And so to decide where a given row of data is going to go, we're going to hash it. Cassandra uses the murmur3 hashing function by default. And so we have the concept of a token ring. Really, it's 2 to the 128 values, but here this is just 100. And so in a given cluster, every node is going to have a token. And that's going to be, here we have 0, 25, 50, 75. Each of these circles is going to represent a node in our cluster. And so when a given piece of data is written, let's say it's hashed and it gets the hash function outputs a value of 3. The token for that row of data is going to be 3, and it's going to belong to this node. The way that works is you're going to do a write into any Cassandra node in your entire cluster. It's going to hash that data, and it's going to go, oh, this belongs to node A here, and it's going to forward that data. So you never need to care about where you're sending data. Whatever node you connect to is going to be able to coordinate that write. When you ask for a given row, you select from table where key equals A. It's going to hash that. It's going to get 3, and it's going to go, oh, I have to go ask node A here for that row. And so we're hashing the primary key here, and not the entire row. So it's a whole bunch of nodes. They're all peers. There is no master. Every node is responsible for a token range. And then so if we have a 4-node cluster, that's sort of an atypical setup, but it looks nice on a slide here. Every node is going to be responsible for a quarter of all possible ranges of data. So you can feel free to interrupt me with any questions at any time. If, for example, this is an intro talk, so if you're not familiar with how hashing functions work, I can step into that and why we can be assured data is going to belong to one of these 4 nodes equally. So obviously, this doesn't get us our availability because if node 2 goes down here, all of that data is now unavailable. So Cassandra has a concept called a replication factor, and that's how many copies of your data are stored. So you typically set that to 3 or higher. So you insert a given row, and let's say it falls in the token range belonging to node 1. That's the node you wrote to. It's going to replicate that to nodes 2 and 3, and then it's going to return a successful acknowledgement back to your client. This is something you're going to set per key space. I'm going to map that to a more relational word later. So with that replication factor 3, each node is actually responsible for 3/4 of the data. Node 1 is going to be holding all 3 of these ranges because these 2 nodes are also going to be replicating what is their primary range to node 1 here. But there is no authoritative sense of truth for a given range. If node 1 and node 4 disagree, Cassandra uses the last write wins policy. So whichever node has the more up-to-date data is the node that's going to be returning the answer to your client. So you can set up an arbitrary number of data centers with Cassandra. That's one of the features it's popular for is it's easy to do global geographic distribution because each of these data centers is an entire ring. A problem that hits, for example, MongoDB, where it partitions replica sets, is if you put one replica set in the West Coast and one replica set in the East Coast, then each of those are going to serve half your data, but based on a partition. So your client is going to need to communicate to both replica sets. Whereas here, if I'm in the East Coast, I can talk to my East Coast data center, know it owns an entire ring of data, and thus it's going to have replicated all possible rows. And then a client in the West Coast could simply connect to its local data center, keeping lower latencies, and be assured that the West Coast data center has also been replicated all possible rows. So this still doesn't get us our availability, because what happens if a node goes down? You fail to replicate. So we also have a per request, a consistency level. And this is you telling Cassandra how many nodes have to respond to my query before it acknowledges me. And so on a write, that's how many nodes have persisted the data to disk. Your options here are things like 1, 2, 3, a quorum of nodes, that's more than half, or a local quorum of nodes, that's more than half in my local data center, or all nodes. And on a read, that's how many nodes I want to read from and then grab the newest piece of data. So if I say wrote a row and it went to nodes 1 and 2, and then later I read a row, I asked for a consistency level of 2 again, and it read me from nodes 2 and 3. 3 is going to say it doesn't have that row. It has nothing from that key because it missed that original write. Node 2 is going to give me an answer, and then the client is just going to receive, here was the response. I was able to achieve it by asking the number of servers you wanted me to. So this is something that's transparent to your driver, and it's that we don't want failure of servers to bring about failure of queries. So as long as you're not using a consistency level of all, it shouldn't matter if servers die. You should be able to lose entire data centers. You should be able to lose nodes. If I have a replication factor of 3 and I'm reading and writing at quorum, as long as 2 nodes are up, I can always read and write to those 2 nodes. And as long as I'm able to repair that 3rd node in time before one of the other 2 go down, I'm able to maintain 100% uptime here. So that's what lets Cassandra handle somewhat catastrophic levels of failure before to the user, the database goes down. Yes?
So I'm confusing these two terms. So replication factor is when you write the data, how many other nodes does it go?
So replication factor is ultimately how many nodes should a given row of data live on. And so you can say just 1, that's a bad idea. You could say 3, you could use a very large number. You could say 100 if your cluster were big enough. That'd be an equally bad idea. The consistency level is a per query concept. It's, hey, on this write, don't acknowledge this as a success until you're sure it's gotten to 2 nodes. Because if, say, only 1 node is down, we might say that that's not good enough, because if I lose that node, I don't want to think that this is persisted, because I want to be able to treat single node losses as no problem. So what might happen is you might have a replication factor of 3, a consistency level of 2, and it only goes to nodes 1 and 2, because node 3 had a network failure and it didn't get the write. Your client got back a successful acknowledgement, and the node not having that data forever. And thus, so Cassandra has to have a number of anti-entropy mechanisms built in, and has to have ways to bring nodes back up to consistency, because otherwise, as we fail nodes, we're going to start losing data, which is something that data store should never do. So the first of those is a mechanism called read repair. When you do a read from a number of servers and they disagree, they're going to give you the correct answer. Here, this is with last write wins, whatever the newest timestamp is, and they're also going to synchronize themselves on that row. The server which had the correct answer is going to send a message to the others, say, hey, you're out of date, here's the correct value. And they're going to get that just as they would a normal write, and it's going to have the backdated timestamp to what the node that does have that data is using, and then so all those nodes are going to be consistent here. Yes?
When the consistency is 1, does it consider the read done after it gets the first response?
Yeah, so for consistency of 1, if you do a read, it's only going to check 1 node.
So that's as fast as possible.
Yeah, you're saying as fast as possible. You're saying I'm willing to get a wrong answer.
Right.
So if we all remember like CS 101, the pigeonhole principle, you can guarantee strong consistency as long as your write and read consistencies sum up to greater than the replication factor. So if you read and write at quorum, always 1 node will be getting you back the right answer. If you read at 1 and write at all, that node will always be correct. Or companies like Netflix have found that the anti-entropy mechanisms work well enough that they can actually always read and write at 1, and they don't care about having gaps where they're inconsistent or wrong. Another mechanism we have is hinted handoffs. When a node goes down, every other node notices. They're communicating once a second. Every node is going to ping a random selection of other nodes in the cluster and go, hey, what do you know about the topology right now? And this is through an algorithm called gossip. It's used in other distributed systems. This happens once a second here. And so it only takes a couple seconds for every node to notice node 3 is down. And so now what every node is going to do is when they get a write that they know needed to go to node 3 and didn't, they're going to store it in a separate file. It's called a hint. And whenever node 3 comes up, they're going to stream that data to node 3. So that window is 3 hours by default. And so as long as a node is down for less than 3 hours, like a quick power failure, a network blip, it's going to stay consistent virtually immediately. But sometimes that doesn't happen. Sometimes nodes go really, really down. And so we have a tool called repair. You run that on a node, and you say, you need to check every other node in the cluster with which you share a range at all, and make sure you're completely consistent. And so they use Merkle trees, which are a data structure that lets me hash what I have on disk, and if you hash what you have on disk, and we can see, my right half of this tree is different from your right half, and I'll stream half my data over to you. And so this mechanism needs every single node to be up, because in order for a node to guarantee it's becoming consistent, it has to check every other node. This is a very slow process. It's a thing an operator does manually. It wasn't until 2014 that we implemented incremental repair, in which if data was already repaired, we wouldn't attempt to repair it again, which was an issue in early Cassandra clusters for those of you who used it back before then. So this might look familiar even if you haven't used Cassandra, because this is Amazon DynamoDB, more or less. The Amazon Dynamo white paper spawned a number of databases like React, Voldemort, and Cassandra, and they all have this model. It's widely considered to be a very good model for a distributed database to maintain availability at the cost of eventual consistency here. So, yeah.
Is there a reason why someone set up the replica factor to value other than 1 if the consistency level is 1?
Yes. So a replication factor of 1 means a given row will only ever be on one server. And so if that server dies, that data is gone forever. But a replication factor of 5, let's say, even with a consistency value of 1, that data will eventually make it to all 5 nodes via those 3 mechanisms that make the cluster consistent over time. So so 1 would never use a replication factor of 1 in production. It simply doesn't make sense for the reasons why someone would use Cassandra. So what does a given node look like? So that was the distributed section. What is a specific Cassandra server? What is that JVM doing? So when a write hits a Cassandra node, the first thing it's going to do is going to be put in an in-memory data store called a mem table creatively, and it's also going to be persisted to disk in a commit log. Now, this is like a write log. It's not a particularly novel thing. And then once both of those happen, the acknowledgement's going to go back. So after a while, this is our persistence mechanism. This is, we didn't ACK a write until it was written to disk in this commit log. But it's not our long-term storage mechanism. So these mem tables, over time, or when they get big enough, typically when they get big enough, are going to be flushed to disk in SS tables. This is a concept from Google's Big Table database that stands for sorted string table. It's just a sorted store of data in key order, which means I'm looking to see if I have a more exciting read path. I don't. When you need to then read that data later, you know where it is by key. You don't know by column. So if I have, key value store and I want to search where value equals 5, I ordered all my data by key. I'd have to check every single file on disk to tell you which rows had that value of 5. which is why you would not use Cassandra for a relational data model, because you would need to set up indexes, which we think of in a relational world as making queries faster, but here are very bad. When you set up an index in Cassandra, you're making it so you don't have to check every file on disk, but because if we remember, not only are these files sorted by key, but actually this whole node was sorted by key. This node only got certain keys. So in order to look up by something other than key, you still have to talk to every single node in the cluster. And that's fine in a small setup where in production you have 3 nodes. But if you're a big company like Netflix, where your cluster is 400 nodes, that's impossible. You could never do it. So the way companies get around that when they need multiple query patterns is to use denormalization and to make multiple tables with multiple key structures and to simply duplicate the data, because the cheapest thing that you can buy in a server is storage. And so why not just store the data 3 times rather than trying to solve a fundamentally unsolvable CS problem is to be consistent and available across all nodes. So this commit log, I lied a little bit. We don't persist that write immediately. We fsync it every 5 to 10 seconds, unless you demand absolute persistence. The thought is if you're writing to 3, 5 nodes at once, they're not all going to fail in the same 5-second window. Now that might not be an assumption you want to take, in which case you're going to demand that persistence, but by default we go for the speed option. So what does the read path look like? So for a given key, we know that it could be in the mem table. We know it could be in a number of SS tables because they're sorted by key. And so we're just going to check all of those. We're going to merge them together to find the newest row of data with that key, because this is an append-only data store. So when you do a write, we're not going to go and overwrite data. When you do an update, we don't go and overwrite data. And when you do a delete, we also don't go and overwrite data. We just append to these SS table files. So when you do a delete, we're going to look in the first one and go, I have the data. And we're going to look at the second one and go, oh no, I deleted it later, so I don't have the data. When you do an update, we're going to go, oh, here it was this, this value was set to 5. And in the next file, we're going to go, oh, the next day it was set to 10, return 10. So that's, eventually would blow our disks out. Yeah.
Yeah, just a little bit confused. You said you essentially tombstone the data.
Yeah.
You leave it in there, you say it's dead.
Yes.
You have to eventually.
I sure hope I have a slide on that. So I don't, so I'll just run that now. So we have a mechanism called compaction. That merges together SS table files because you're going to be having overwritten rows. And if we have a row and an update to that row, in the newly merged file, we're only going to have the update. In a delete, we're just going to leave the tombstone. We're going to actually have scrubbed the original data. So, but we still have to leave the tombstone. And the reason we have to do that is because if I got a row and a deletion, and you're another node, and you just got a row, I can't purge that off disk, because then you're going to say, no, that data's still there. So I have to persist my delete marker, which is, we call it tombstone, and I need to do that until I'm sure that tombstone has been replicated to every single node. And so deleting data is actually a long process in Cassandra. The default for our garbage collection here and making sure data is actually scrubbed is 30 days. So if you're have some sort of compliance mechanism which you I absolutely must be able to delete data within X days, that could be difficult for you, in which case this might not be the data store for you. So the way compaction works is we have a large number, 4 algorithms now that you can pick between, and they merge these files in different ways. By default, it's size tiered, and so it'll take the 4 smallest ones, merge them together, and make a medium one. And then once there are 4 medium ones, so it's picking 4 files that are within 10% of each other in size, and it's just plunging those together. And so we have very few files on disk, so on a read we have to touch as few files as possible. There are others like leveled compaction, where we build a pyramid structure, so you know that a given read is only going to touch a number of files given to how many pyramid tiers you've built, we have something called time window for if you have a time series files or you're doing sensor data, then we can say, oh, you need this time slice. These files only touch that time slice. And that allows us, Cassandra is actually really popular amongst those sort of use cases, and that allows it to be very performant in reads for those use cases. So what is, yeah?
Can you explain one more time the SS tables, how the indexing works? And what makes it so expensive to go through?
So, yeah, just a second. So a given SS table is going to have in its header what range of keys, what primary keys it owns. So, just sticking with ints here, this file might say I have keys 1 to 15, of which it really only has 1, 6, 9, 15. This might say I have 1 to 30. And so when you say select from the table where key is 10, it's going to go, all right, well, damn, it could be neither one. Then each of those is going to have a Bloom filter that was written out. That's the data structure that tells you if data is in a set, and it can either do guaranteed negatives or maybes. So it has a false positive rate but no false negative rate, which is, false negative rate would be terrible in a database. So it's going to say it's maybe in here, and it's going to say it's maybe in here, in which case we have to check both. And then we have this is assuming you've blown through all the caches in Cassandra, of which there are many, and I don't know how all of them work. But so from then, we're going to be able to we have an index in the file, and we can cut straight to where the set of rows where the key is 10 are in the file, and we can just read all those. And so the reason we can't just check the value is because absolutely everything is indexed by the primary key here. And so we would need to check every single file on every single node in order for you to do an arbitrary select by a value. So we allow you to create a secondary index, which is where you say, hey, index this one column because I really need to look up by it. In which case you still have to check every single node, but you don't have to check every single file. Because for every single SS table file, we create a corresponding index file that indexes that same SS table, but by that column you indexed. And then that way you can more efficiently search on a given node, but you still had to check every single node. Recently, like last year, we add materialized views, which are a way to automatically do that denormalization that many companies had to or still prefer to do manually. So you could say, hey, I have this table, create a matching view on that table that's indexed this other way, so I can query it in a different way. And that is much more efficient because that's still, now you're still searching by a key of that new view, and so you only have to select a subset of nodes the way you would with a normal query. So Cassandra, if you touched it a long time ago, used to have a terrible, disgusting client interface. It used Apache Thrift, and it was really unpleasant, and everyone hated it. So we moved to a subset of SQL, which we call CQL, to be very explicit that this is a subset of SQL because we're a non-relational database and we can't handle all of SQL. We don't have joins or anything like it, and so on for a very long list of things. So what do our structures here look like? We have a key space. This is like a database or a schema, depending on what relational DB you're using. And this is just a bag of tables. You put a number of tables in a key space, and the thing a key space defines, it only has one option, and that is the replication strategy. So a key space, which is just a selector for a group of tables, you tell it what the replication factor for those tables is. So you can say every single one of these tables has an RF of 3. Every single one of these tables has an RF of 5. More interestingly, you can say every one of these tables has 3 RF of 3 for my European data center and not in America. Don't ever send this data to America, which is a common need because of European privacy laws. You can say I need 1 copy of this on the West Coast, but keep 5 copies of it on the East Coast because that's where my big data center is. So you can do that all the way down to like the rack level. We let you specify a given node what rack it's on within a DC. These are all logical constructs. When you tell a node it's in a data center, you can lie to it, and it's going to be confused because latencies aren't going to match. But things don't actually have to physically be on a rack for you to label them all the same rack. In AWS, you can make a rack an availability zone, and you can make a data center an entire region. So we have tables. You know what a table is. Table has a primary key defined, and it has columns defined, and you insert data. So we also have partitions and rows. So before this, I just talked about rows, and really we aren't partitioning data based on the primary key. We're partitioning it based on the partition key, which is a subset of the primary key. So you can say this is my example, for this table events, where I have a column which is the package ID, a status timestamp, a location, and notes. This is my primary key. It's the compound of the package ID and the timestamp. The partition key here is just the first one. It's just the package ID. So all rows with a given package ID will get partitioned to the same node. But I can have any number of rows in this partition as long as they have different status timestamps. And I can keep compounding this column as far out as I want. And so that lets us decide how data is partitioned together. Well, it's a way to group rows, essentially. So some people, if they have tables where they don't have a nice way to do this, where it's all of these timestamps for a given package, and some people just use UUIDs as their partition key. This is what the query language looks like. Create a key space, give it a replication factor. Just do 1. That's a terrible idea. Do 2 in each data center. That's a much better idea. Queries look like you would expect queries to look like. You do inserts, you do selects. That's pretty standard SQL. So transactions, we don't have those. Those are real hard to do. And so when you do an insert, you're saying push it out, and it's going to go out with the timestamp that I sent it out at. And so someone else could do an insert at the same time, and it's just whoever wins by a microsecond. You can say, hey, update this, and it could not be there yet. You could say, there was no update this if it's set to this mechanism. And so we have a very, very minor subset of what one would want from transactions, which we call lightweight transactions, which is not a reference to their performance. It's a reference to their functionality. These are bad. And so these are for the use case where you have a users table. That doesn't happen very often where you get a new user, and so you can say, hey, insert this new user only if there isn't already one. And this uses Paxos under the hood, if you're familiar with that consensus algorithm. And this gives us linearizable consistency. It lets us serialize inserts, and so it lets me say, hey, insert this new user with this password only if someone doesn't exist. And if once I've gotten that lock, no one else can do that insert. And then so if 5 of us kick it off at the same time, only one of us is going to get a success. Everyone else is going to get a sorry. Someone else contended you for this at the same time, and you lost the Paxos debate. So returns a column called applied, which tells you if it worked or not. So it'll tell you that the write worked but didn't get applied. It'll say, hey, it made it to all the nodes. They're all up. They're all there. But they didn't let you do this. You said insert it. If it doesn't exist, it did exist. You can do things like update, set column equals X only if it was Y before. So you're not going to get something like a primary key violation exception or any kind of exception when you try to do a faulty transaction, because we don't have any read before writes. This is our only read before write mechanism, Cassandra. Yes?
So whenever you do an update, you're
Yes.
able to query inside of the row in order to limit that?
Um,
Or is that super slow?
Yeah, no, so this is essentially a read before write, but with a locking inside the database. Yeah.
So the condition does or doesn't have to be the key?
The condition does not have to be the key.
Okay, because you do the read.
Yeah, because you do the read first. So what kind of use cases is Cassandra right for you? So here's a non-typical Cassandra installation. This is Apple's. This is the biggest known one in the world. They have tens of petabytes of data sitting in 115,000 nodes, doing a lot of ops per second. And they're on a 5-year-old version because they're a big company, and so they update slow. If you need that scale of data, I don't know another database for you. You can't put that on a MySQL box. You can't. You'd need a really, really, really big SAN to get that in Oracle. These are all consumer SSDs and regular servers. The Apple's guys are all really frequent contributors to Apache Cassandra. They're very open about this setup. Not open about what it backs, but there's only so many programs they have that this could be running.
Why do you say you don't know? Like, so you wouldn't consider like HBase or something like that?
Um,
Able to handle that?
HBase is much slower read and write throughput. But you're fair that since it sits on HDFS, it can handle that level of data density. Cassandra is pretty bad at density per node. It's fine at density cluster-wide. HBase gets way more dense per node, I know that.
Right, I can tell from the nodes, like only tens of petabytes for 115,000 nodes. Like, how much is that per node? That's obviously not a lot, right?
Yeah,
So it's pretty sparse.
2 to 10 gigabytes per
Oh,
node.
God, okay.
Yeah. No, terabytes, a completely different level. Yeah.
And then, sorry, step back a little bit. A node, is that an instance on a server?
Yeah, so that is
Or is it a server?
that's a JVM instance on a server, but that typically also is a server.
Is it a 32-bit JVM or is it?
64.
Okay.
Yeah.
So it does have 32 gig memory limitation.
No. No, it doesn't. The reason that it's typically a server and not an instance on a server is because Cassandra nodes hate when you share the storage, because since they're doing append-only writes virtually the whole time, they will hose a SAN, absolutely destroy it.
But what if you had like 2 separate RAIDs on one server and you just had...
Oh, multi-tenancy like that, yeah, that would work. Yeah. I mean, it's not particularly common, but it would work just fine. So Cassandra is good when you need this kind of scale, when you need to blow up a cluster that big, because it's hard to handle a relational database at that scale. You can only do so many masters in a relational setup. But if you just need a really big box, probably Postgres, SQL Server, MySQL, etc. are right for you. If you like, the 100% uptime is nice, but the non-relational data model is not. So this is a incredibly powerful tool, but it's a specific one. I think it's the best database, but it's also the worst because like no one goes that big, but maybe no one else needs to go that big. There are companies like Netflix which only uses Cassandra now. They don't have any other databases. They don't use Oracle for anything anymore. So this is a sufficiently versatile data store that it could handle, whatever you need. But if you don't need to leave a single box, it's much easier to administer one Postgres instance or one MySQL instance. And a relational data model is something that's much more familiar to most developers, and ORMs exist for all of us, like all relational databases, and you have to use just the Cassandra ORM. And so this is not a niche tool, but not a one that I would say rush out to adopt. Not much like something like Mongo is a fun thing to play with at home, where like this is less pleasant to play with at home because a one node cluster doesn't super make sense. So if this does look interesting and you wanted to try it out, you download it from source. It's an open source project, Apache 2 licensed. It is an Apache Software Foundation project. You can get binaries installed from the DataStax website, or probably from Apache. I'm the maintainer of CCM, that's the Cassandra Cluster Manager. That's a tool that is actually really popular, and developers use it to simulate Cassandra clusters on one machine. So, you can do this, and it's going to spin you up 3 JVM instances all running Cassandra version 2.0.1. It's going to configure them for you, and it's going to look like a real cluster. It's going to use the loopback addresses, and all of those nodes are going to think they're separate nodes running a whole cluster, and it's one little toy you can play with on your laptop. But it is 3 JVMs, each contending for several gigs of RAM. So if you're not you don't have at least 8 on your laptop, it's going to be unpleasant to use. We're on IRC, Cassandra on Freenode, Cassandra-dev, DataStax-drivers. There's, like any Apache project, active mailing lists. Stack Overflow I found relatively unheard of project locally here, but it's very popular, and you won't have issues finding resources for it. So more formal Q&A here. Yes.
What's a typical read pattern when you have these large clusters? Do they use SQL, or do they have other things on top of it like Spark that do analysis?
Both. So a standard Cassandra cluster, you're just going to be using CQL to do your reads, but DataStax, the company I work for, we sell like in the high-level enterprise version that integrates with Spark. That's very popular for doing analytics work like you've asked. I worked on the analytics integration in Cassandra, so I'm somewhat familiar with that, but not actually familiar with the Spark end of it. But people use Hadoop, various Hadoop things, Hive, Pig. Spark is not really Hadoop to do analytics on Cassandra without actually needing to do it on HDFS.
So you have Hive
Yeah.
for Cassandra?
Yeah. Yes.
So you've shown that Apple needs Cassandra. If you were maybe not terribly concerned about availability, at what point would you start considering Cassandra?
So it's really nice for that geographic distribution. So if you need to easily partition worldwide and you want like the active for as long as I keep saying that, you can set up 5, 10, 15 data centers, all active, all handling reads and writes, locally, which is a really cool thing. You normally can't blow past active in most databases. That's one reason. There's that scale. You might find the availability nice, but if you don't need any of those things, then you probably don't need to chew off the new data model to learn.
And does that cluster manager, can you simulate latencies with it?
It doesn't, but nothing's stopping you from using a similar tool.
Okay.
Like it'll spin up the server, and then you can use something to fake in the latency. Yeah, on top of it. Yes.
If you're running out of space and you need to add nodes and rebalance the data on a cluster,
Yeah.
how do you go about doing that?
So you can. There are, I guess, a lot of operations, but so there's nothing. As you add a node, it'll contact all the other nodes in the cluster, and it'll go, hey, I just started up. Here's either the token I was started with, or I'm gonna, randomly pick a set of tokens, and please stream me data. And this is a bootstrap process. So during this, it's gonna be taking writes but not serving reads, and eventually, once it's finished streaming in all data from all the other nodes that it shares ranges with, it's just gonna become a live member of the cluster. You can add up whole data centers at once. You would spin up all the nodes. You would connect them to the cluster. You would have told them they're in this new data center. Let's call it DC2. You're then going to go into all of your key spaces, and you're going to say, hey, you're only replicating DC1 right now. Add in a DC2. And then you're going to trigger a function called rebuild. And all the nodes in DC1 are going to stream all their data over to DC2. And then once DC2 is finished rebuilding, the replication factor that you set up has already been seeing the writes make it over to the second DC. And then at any point, you can just go into your client application and change your whitelist policy to say, hey, also read from DC2 now. And then that's a way to mass add nodes. There's decommissioning, where you can tell a node to shut itself down, stream all its data to the new owners of its ranges. It's very easy to flex up and down.
What are the limitations of the Apache distribution of Cassandra compared to the DataStax distribution?
So the Apache distribution is Cassandra. The DataStax distribution is essentially only other things. So we bundle in Solr for full text search on text columns, and we bundle in Spark for analytics. And so this all just looks like CQL queries to you. But the underlying database, Cassandra, is exactly the same in both systems.
So I can use the plain
Yeah. Yeah, yeah.
Do you have any advice for thinking about partition keys, and then like what are good ways of looking at how to come up with ones that are useful?
So the generic advice is, you have your table and all the columns you want, and it's how are you going to want to read that data? And that's going to be how you need to make the tables you to normalize, because you're going to read based on either partition or primary keys. And it's thinking, like it's thinking hard about whether you need to be able to read from every column, because usually you don't, and sometimes it's unpleasant, but it's not impossible. Beyond that, I've done data modeling help with some companies, and honestly, it gets to you need to show me your tables, and I can help you out. It can get very specific.
There's those three methods that you mentioned for repairing consistency problems.
Yeah.
Does it keep statistics about those, and how often or how much in general are things out of sync?
So every node is going to know what mutations, writes, or updates it dropped, as then like it was sending and timed out, or it was handling itself and it screwed up. And so you're going to know, it's going to keep track of hints it sent. So as far as read, repair, and hints go, you're going to know how often those kicked in, how much data those sent, how much data was being dropped. As far as repair goes, that's normally catastrophic failure, like I lost a disk, or that's I've only been reading and writing at quorum this whole time, and now I want to make sure that third node, that last half, actually catches up. So you're going to be kicking off repair manually, and when that repair finishes, it's going to tell you how much data was streamed and how much data was mismatched. But it's very crucial to this working at all that at a given point in time, a node doesn't know what all the other nodes have. Because nodes are at no point guaranteed to be consistent until at the end of a repair just finishing.
Do you usually run repair like every month or every day?
Yes. So you need to have essentially repair finished across all nodes. Like that period has to be less than whatever you set the garbage collection delay for tombstones to be recycled to, which defaults to 30 days. So normally a cycle of repair across every node is finished within 30 days. So whatever that means to your cluster, if it's big enough, that means I'm running it every day on one node each, or that means, on Monday I run it on my first node, like the next Monday I run it on my second node, if you have a 3 to 5 node cluster. We sell and used to have a free version of an operators like a dashboard into Cassandra where you could set up an automated repair service, and it would repair based on token ranges. And so it would just say, all right, repair across all nodes range 0 to 10. And as soon as that's done, just kick off 10 to 20, and it would just walk that as fast as physically possible. That's what most operators end up doing themselves, is setting something like that up, is keeping repair going constantly.
What is the underlying hardware? How is that normally configured on a server? Do you just have a bunch of disks connected into like HBA? How do you know that you lost a disk? Do you lose a disk, or do you just lose a node?
So losing a node is a separate thing. You could just spin up a new node, whether it's on a separate server, the same server, and tell it to rebuild in place. But losing a disk, however, you normally, as like a sysadmin, know that a disk failed. There's nothing in Cassandra there other than exceptions that all of a sudden the files it thought were there are gone, to inform you of that.
So do people set up, RAID or complex RAID arrays
So the disk-wise, the ideal setup is every node is running on its own server, and those have local SSDs. And normally people just throw those in RAID 0, honestly.
Are there any the node failure modes that Cassandra isn't very good at handling or dealing or recovering from?
Well, so if you have a particularly dense cluster, so you're running, past 10 terabytes, you're trying like 10, 15, 20 terabytes per node, it takes a lot of time to stream 20 terabytes of data when a node fails to replace it. And so, frankly, in addition to that, being time intensive, Cassandra's not super great, so it's at that, so it's not running at, say, like the width of that link. So replaying dense nodes takes a long time. Bootstrapping new real dense nodes takes a long time. In terms of failure resiliency, no, not particularly.
So when you say that Cassandra maybe can't fill that link, are you assuming like a 10 gig link or a 1 gig link?
I'm assuming 10.
Okay.
Yeah. All right. Thank you, everyone.